I'm going to talk about open silicon a little bit here. So I just went out to Singapore for our first run. I'm working with wafer.space, and we are doing open silicon. So I will pass this around if you guys could be careful with it, but this is the first run. And this is an actual piece of silicon that we had made. So just a quick primer here. What is silicon? Silicon is our CPUs, GPUs, memory. You can do it to make radios, all kinds of different circuits. It is what runs Python. So anyways, Tim and I, we went out to Singapore and we got our wafers. And I also built a Python-based sorting robot that takes the projects here and sorts them up. I will talk a little bit about what that means now. So basically, in the circuit board world, in the past, it was difficult to get circuit boards made. So Oshpark came along, and what they basically did was they took a bunch of people's projects, they put it onto a big panel because none of the manufacturers actually wanted to talk to individuals. So it was like impossible to get circuit boards made by just users in small quantities until Oshpark came around. So basically, that's what we're doing here as well. The wafer that you saw there, we take 40 people's projects, we go ahead and we throw them on a wafer, and then we get 25 wafers, and everybody gets 1,000 of their chips. So there's all kinds of different designs. There's also tiny tape outs. They do one, they take one of the dies then, and they divide that up 160 times so that we can improve access to silicon and designing computers and whatnot. I'll just talk briefly about a couple of the interesting projects that are here. We have Ishii. They're doing a bunch of analog work, which is also another super cool thing that doesn't really exist because it's so difficult to work with. But they have a bunch of op amps and silicon-based inductors and capacitors and stuff that they're testing. We have Tholen. Because this is open now, you get a bunch of the artists who come in and do really neat things. This chip also has a number of projects on here, some DACs, but it also has the sound chip from the old Commodore and a few other now deprecated chips that we're going to start seeing that people can get access to again. Here's another one with a piece of logo on it. This one also has a little computer that you can kind of see below the picture there, and that will put on the logo onto a VGA outlet if you plug that in. So that was everything that we did in Singapore. Dies themselves are very difficult to work with. Everything is super tiny, as you guys see as I pass this around. You basically can't even see the pads that you need to wire to. So in Shenzhen, we worked with a bunch of wire bonders, and we were able to now take the dies themselves, wire them to a larger PCB that has a connector on the back. So now somebody who wants to do something with their chips can use common components and get JLC or any of these companies to populate your board with a mating connector, and you can just stick your chip on there. We have a couple of pictures of just the wire bonding process as it goes. A couple of close-up shots of the wire bonds of what they look like. And some of the neatest things that comes out of this, there are all kinds of very interesting projects and everything like that. But the one that really kind of caught my eye is over time, we've been shrinking our nodes. So, now TSMC, if you're familiar with that, some of the leading edge ones, they're down, in the angstrom range, which is down below the nanometers. But, back in the 90s and 2000s, you remember computers got faster very, very quickly. And within a couple of years, your computer was basically a piece of garbage. And basically, what we were able to do here, just again in the first run with people being able to be creative with what they're doing, because it costs like any company who wanted to make their own wafers, it's going to cost them like $1 million. But anyways, this is 180 nanometer for the wafer that you see going around here. But the designers and everything like that have really been able to squeeze the performance out of that to the 90 nanometer range. So there's all kinds of really cool things that are coming down the pipe. I want to keep this short. Wafer.space as their second run. You can go ahead and look at them online. They're on Crowd Supply. Could really use your support if you want to see open silicon stay. And if there are any questions,
the question about the second is how much storage capacity it can have in this one.
So that's kind of one of the neat things. So Global Foundries and the PDK, like the design kit that you're handed when you get this, only had 5 volt tolerant RAM. And I can't remember what it is. It's down in like the few K range. But basically, because they were able to be smarter about some things and drop it down to 3.3 volts, they got 40% more RAM in the same space than you would. So you're just like in kilobyte range
Only
for the size of dies that you saw there.
Not ChiPy level. Terabyte.
Kilobytes.
No, okay. So
Tens.
How much does this cost?
I mean, that's like hard to say, right? So the silicon itself, and to get that done, I want to say it's somewhere around $150,000 to get 25 of those wafers. Now, this is kind of assuming that you already have a relationship with the fab, that you already have relationships with all kinds of people. Tim Ansel is the one who started wafer.space, and he originally had started with Google, so was able to create a lot of these networks through his time at Google, and was able to open some of the doors to get all this going. Saw a question over here.
Yeah, you mentioned that someone was doing some analog stuff on this wafer.
Yeah.
As I understand, typically you have to, for an analog circuit, you have to take a laser and trim the resistors and inductors and such.
I mean, no. I mean, there's like a range of like, if you draw it like this, the fab will promise that they will, make your wafer within some percentage of like what you drew. So the analog stuff, basically, we're still in the world where you're like drawing pictures of your transistors and stuff like this. It's very, very basic. But then like if you design something, there's like a window of the tolerance. And if you want to get finer than that, then maybe you'll have to go do some like fancy stuff. But other than that, like, what you get will be, I'm trying to think of the name of it. What you are talking about, though, we do have somebody who's doing some cryptography stuff on one of these other dies. And I can't remember, puffs, I think is what it's called. And basically the variability in the processing of the chip is used to generate your cryptography keys. So like exactly what you're saying there is like some variability, and then some people want to use some of that variability to generate keys, like I'm saying. And there are some problems and stuff about doing that, but like, I hope I answered your question. Any more questions? Cool. Let's take a 10-minute break.